All right, so next up, we're going to look at different peaks and see how this helps us identify which compounds there are. And so there's pretty much only two that I want you to memorize, the alcohol and the carbonyl peak. The rest, I don't think are really that important. You don't have to memorize them. You can always look them up in charts. So I grabbed this one off the internet. I like this one because it kind of shows the little examples of what the peaks look like, but you can use any kinds of IR charts, right? So if you Google IR functional groups chart, right, you can see down here on this bottom left, there's the one that I have right there, but you can get other ones as well. Here's one from Sigma, right? This one's extremely detailed. You see there's all kinds of stuff. Not really that useful for our class. I mean, you see it's just too much. I don't like that one too much. This one's better. It's pretty good. I just don't like the formatting of this one. I like this one the best. And this one came from this third link from this UCLA. So if you Google IR absorption table and UCLA, this one will come up. The reason I like this one is because it's nice, short, and sweet. Right on the left here, you can see which functional group is. On the characteristic absorption, you can see what wave number it's going to absorb at. The MS or V stands for the peak strength. So M is a medium peak strength, and so it's not a very big peak. S is strong, which means that it's a really big peak, and V is variable. So it just kind of depends. And then some notes, right? Just some notes on real quick ones, right? So on this alkyl CH1, it just tells you that, hey, most organic compounds have CH, and so it's not actually that useful to figure out. Right. And we'll go through some of these depending on kind of order of importance. Right. And so the first one we're going to take a look at is the OH peak. This one's probably the most important. And so it shows up around 32 to 3,400. And it's a very broad peak. So let's take a look at some examples of that, right? So here's the IR spectra of isopropyl alcohol. You can see it has this OH, and you see this big fatty right there. That's the alcohol right there. This is 1-hexanol, which is also an alcohol. So it's just hexane with an alcohol there. And you can see it's got this big fat alcohol peak on it. And then this is ethanol, right? This is the alcohol that you drink, right? And it's got this big fat ethanol peak, right? That they actually label as the OH stretch, right? So if you see this big fat peak over there, chances are you have an alcohol. We'll see one that's somewhat similar, but not too similar. And so naturally, you might be thinking, why is this peak so broad? And the answer to that question is hydrogen bonding. So we have this OH, and then it can hydrogen bond to another oxygen, hydrogen. And so this bond length can actually vary quite significantly. It can be long, it can be short, and that way it can be strong or it can be weak, which causes this broadening of this peak, right? So that's what causes this right here. One thing to note, though, it does depend on the environment. So you can see this one has an alcohol, but this is a very sharp peak, right? And the reason that this is a sharp peak is because this is in a very non-polar solvent that can't hydrogen bond, and they have it very dilute. And so basically hydrogen bonding can't occur. I won't ever show you spectra like this, but just in case you find it online, that's why it's not broad. I'll always show you as these broad peaks right here.